Hello everyone. In this section we will be covering measures of variation, and here by variation we actually mean dispersion relatively or relative to the mean or x bar. I told you that everything is going to be related to x bar. The first measure we're going to focus on is the variance. There are several ways to find the variance, but this is the fastest formula to compute the variance. So this is the formula that we'll be using. Notice that we have two formulas for the variance. One is for regular data, and the other one is for group data. You can also find the variance using the TI-83 or 84, and I'll show you that in section 3.3. For now, we're gonna deal with this formula first, and then this one. It looks different, but it's pretty much the same formula. Just remember, this is for regular data, and this is when it's given to you in group data or when it's given in classes. A few things to notice about the variance. Remember, from algebra, whenever you square a number, the number always has to be positive. So therefore, s squared always has to be positive. If you get a negative value, that means you did something wrong. So therefore, this one is also positive. Let's do an example and see how you can find the variance using this formula. So let's go back to the example we've been using all along in chapter 3. So this is the data from before. So this is what is given. This is regular data. So the first thing you should do is create a table like this. So this is the given data. In the next column, all you have to do is square the value. So 2 squared is 4. This is 9. This is 25. This is 49. And this is 100. Then find the sums like we have done before. Remember, the sum of this one was 27, and the sum of this one is 187. So you should check, stop the video and check that these are the values so that you get this number. Remember what this means. This is the sum of x, and this is the sum of x squared. So let's rewrite the formula again. Remember, the variance is the sum of x squared minus the sum of x, the whole thing squared, divided by n, which remember n is the sample size, which in this case is 5, and everything is divided by n minus 1. So that's the formula. So when we plug in the values, this should be 187 minus 27 squared divided by 5, and then everything is divided by 4. Make sure you follow the order of operations, the pandas thing, and remember that the answer has to be positive. You get a negative value, something is wrong. So this is what we have. We have 187. The first thing you have to do is square this value, then divide by 5. If you do that, you will get 145.8, then divided by 4. So this part gives you this part, so you should check that. Then this is equals to 41.2 over 4, which is equals to 10.3. Now, the thing that we really want is not really the variance, even though we're going to use the variance many times. What we really want is S, which is the standard deviation. You're going to be seeing this many times too. So S is the square root of the variance, which always has to be positive. So in our case, this would be the square root of 10.3, and that's around 3.2. Now, the standard deviation is probably one of the most important things on the class, And I told you already that X bar is very, very important. So these two animals or players, whatever you want to call them, are going to be the most important things in when it comes to statistics. Now, the standard deviation is actually a measure of the dispersion of the data related or relative to the mean. So therefore, the bigger the standard deviation, the more dispersed things will be. Now, there is an analogous to finance, if you ever took a finance or economics class, where they talk about the stock market and they have something called volatility. So the more volatile a stock is, that means it has a big standard deviation. And if the standard deviation is small, that means it's less volatile. So the standard deviation is going to be very important, like you will see in chapter 7, 8, 9, and 10. For now, the main idea is if you want to find the standard deviation, you find the variance first. And once you find the variance, take the square root. And in the next slides, we'll see how we use the standard deviation to measure the dispersion related to the mean. Like there are some rules or some specific things that need to happen all the time. And that's going to be the beginning of statistics. All right, let's go to the next page. Recall from section 3.1 that the data can be given to you in a form that looks like this. Remember that this part has to be given all the time. In the previous sections, we find this. Remember, to find the midpoint, you add this 2 divided by 2. You add this 2 divided by 2. We also find this one. To find this column, you multiply the frequency times the midpoint. So 6 times 3 is 18. 10 times 8 is 80, and so forth. Also, remember last time in the section 3.1, we didn't want to add this, so don't add it. We don't need it. Recall from last time that the sum to this one was 168. So we already have done that. So now, how do we find the value for the last column? Well, this part is telling you exactly what to do, but let's break this down. This is telling you to square the midpoint, then multiply times the frequency. So in this case, the midpoint is 3. So you will need 3 squared times the frequency, which is 6. So it will be 9 times 6, which is 54. So that's how we will get these values. So the first one is 54. The next one is going to be a squared times 10, which will be 64 times 10. This will give you 640, and so forth. So the next one will be 13 squared times 4. This is 169 times 4, which is 676. And then the last one is just 18 squared, which is 324. Then if we add all the values, we'll get 1694. Recall that the formula for group data is the following. So we have all the information. All we have to do is now is plug it in. So for example, the sum of the frequencies times the midpoint square is this value. The sum of the frequencies is this value, and square. And then the sum of the frequencies is 21. So all we have to do is plug it in. It's very similar. Actually, it's the same as the last formula. It just looks a little different, but it's the exact same thing. So this will be 1694 minus 168 squared divided by 21, and everything divided by 20. So be careful with the calculator. Once you compute everything, this should give you 17.5. Remember that this is the variance, but usually what you want is the standard deviation. So the standard deviation will be the square root of that. And you should run all the answers to at least 2 decimal places. So the square root of 17.5 is 4.18, and this is the standard deviation, which is what the measure that we'll be using mostly. The next measure relates just the standard deviation, which now you know how to find, and the mean, which we found in section 3.1, and you had to write the answer in percentage. For example, let's say that you have a data set where the standard deviation was 4 and the mean was 10. So then the coefficient of variation would be 4 over 10, which is the same thing as 0.4, which is 40%. So the coefficient of variation of this set will be 40%. Let's say your cousin Pedro has a different set where the standard deviation is 6 and the average was 18. So in this case, the coefficient of variation will be 6 over 18, which is equals to 0.333 and so forth, which is around 33.33%. Like we said before, the standard deviation measures the dispersion. So the smaller the standard deviation, the better. And better just means is that data is less dispersed, which means you have more control over the data, or your predictions potentially will be better. Less dispersed means better predictions, and you'll see what we mean by that once we get to chapter 7, 8, 9, and 10. All right, let's move on to the next slide. Chebyshev term is one of the most important terms to tell you how the standard deviation will be related to the rest of the data, or more importantly, Chebyshev theorem tells you how data has to behave regardless of what kind of data you have. So this is a formula that will tell you the proportion that has to lay within k standard deviations. The value for k is given to you on the question, because that's pretty much what the question is asking you. What will happen if you move 1, 2, 3, 4, or whatever standard deviations you want? So for example, let's say that k is equals to 2. Okay? So that means you're moving 2 standard deviations. Now here when we say 2 standard deviations, we mean 2 standard deviations to the right. So this is 1 standard deviation, 2 standard deviations. But it also implies that you're moving 2 standard deviations to the left. So when we say 1, it means from here to here. And if it says 2 standard deviations, it's from here to here. So let's start with k equals to 2. Remember that k is just the number of standard deviations. So there is nothing special about 2. It could be any value. But you will see that after k equals to 4, there is really no point of going any farther. Now, if we plug this into this equation, this is what happens. We get 1, 2 squared, which is equals to 1 minus 1/4, or 3/4, which is 75%. So what that means is that 75% of the data, doesn't matter what kind of data you have, has to be within 2 standard deviations. And this has to be true no matter what kind of data you have. Now to make this example more concrete, let's say you have a class where you have 100 students. And let's say the average for the class on the final was 70, and then the standard deviation was 4. Okay? So therefore the average was 70. So you move one standard deviation to the right, it will be 74, which is just 70 plus 4. If you move one more, it will be 78. If you move one to the left, this will be 70 minus 4, which is 66. Then 66 minus 4 will give you 62. Okay? So what does this really mean? Let's say that every student is represented by a dot. Okay? So let's say the first person got a 62. The other guy got a 64, 66. Somebody got 70, somebody else got 70, and so forth. Somebody got 78, somebody got 80, somebody got 90, somebody got 20, and so forth. So in total, you need to have 100 dots. Why? Because there is 100 students. So what the Chebyshev theorem tells you is that doesn't matter where the data came from, if you move 2 standard deviations, which in this case will be from here to here, that between those 2 points you need to have at least 75 dots or 75 students. If that's not the case, that means that there's something wrong with the data. Either the mean or the standard deviations are wrong, or the data is not related to this mean or standard deviation. Like I say, there's nothing special about k equals to 2. Let's say that if k was 3, and we plug it into the formula again, now we will have 1 over 3 squared. So this will be 1 minus 1 over 9, which is 8 nines. And this is around 88%. So therefore, if you move one more standard deviation, so now this will be 82. And if we move one more to the other side, this will be 58. So therefore now between here and here, you need to have at least 88 students, okay? Regardless of what kind of data you have. The last part of this section is called the empirical rule. And the empirical rule is actually a special case of Chebyshev's theorem. Chebyshev's theorem is always true. The empirical rule is not always true. But the empirical rule is so important that pretty much the whole class is based on the assumption that the empirical rule is true. The empirical rule is also called the normal distribution. And we'll see this in a lot of detail in chapter 6. So what does the empirical rule says? The empirical rule says this, that you move one standard deviation, which will be from here to here, to here, you should have at least 68% of the data. If you move 2 standard deviations, which will be from here to here, that you should have 95% of the data. And if you move 3 standard deviations, which will be from here to here, that you should have 99.7% of the data. So as you can see, there is no point to move more than 3 standard deviations because you technically have everything at 99.7. Now, one thing that is very important about the empirical rule is that it gives you an idea of what normal is supposed to mean. So we're going to use 2 standard deviations as the basis. So if anything is 2 standard deviations away from the mean and the distribution is normal, or if the empirical rule applies, that means that anything that is within 2 standard deviations, which should be from here to here, is considered normal. For example, let's say that you go to a supermarket, and in the market they say that there is a particular fish where the average weight of the fish, that the average weight of the fish is 10 pounds. And let's say that the standard deviation is 2 pounds. So now, let me ask you a question. If you go to the store and you buy a fish of this kind, and they sell you a fish and the fish weighs 7 pounds, are you going to be happy with this? The answer most likely is no, because you will feel you are cheated. But if you use the empirical rule, what the empirical rule says is that if you move to standard deviations, which this will be 12, this will be 14, this one will be 8, and this one will be 6. The empirical rule is saying that anything between here and here is normal. So therefore, if the fish weighs 7 pounds, then that's totally normal. Now, if the fish weighs 13 pounds, you're probably not going to complain, but it's also completely normal. Now, if the fish weighs 80 pounds, then it's probably not a fish, and I'm sure you will not complain. So this is what we're going to call very soon outliers. This doesn't fit the mold. Now, what about the fish weighs 2 pounds? Well, then you probably will not be happy, and now you have an argument to say, well, this is now within 2 standard deviations, so therefore this is probably the wrong fish, and you can go to court and win. But if you go to court and argue that a 7-pound fish is not of this kind, then you probably lose, because according to the empirical rule, 95% of the fish has to be between 6 and 14 pounds. Okay? All right, so that's the end of section 3.2.